So number 3, more equations, but we kind of have to do them because in order to determine the answer to number 5, we have to do numbers 3 and 4. So what I'm going to do is I'm just going to crank these out real quick because number 3, they just flat out gave us the displacement vector. All right, they told us ABC, and they told us the point. So x sub O, y sub O, z sub O. So 3 minus t, 1 plus 6t, and 4 minus 3t. All right, so the second one, find the equation of the line containing. So I need to figure out my ABC, the parallel vector. So parallel vector, again, displacement vector. So 4, -3, 5. All right, so this makes this my x sub O, y sub O, z sub O. So I'm looking at 1 plus 4t, 1 minus 3t, and 2 plus 5t. All right, so those are my my parametric equations representing the lines passing through those points. Great. Now I want to figure out if they're going to intersect one another. All right. So this is where things get a little interesting because there's a couple of different ways that this could play out. But I'm going to kind of lead you to the most appropriate way to do it. Okay, because they're asking for the intersection of two lines. All right. Now, units are kind of an important thing here. I mean, they're more than kind of. They're definitely an important thing. Right? The fact that the units were not defined tells us that we don't know that these are kind of operating on the same time frame. So the first problem could be working in hours, and the second problem could be working in minutes. Right? Maybe T doesn't even represent time at all. Maybe it represents temperature. One's in Fahrenheit and the other's in Celsius. Right? The idea is that not all T's are going to be created equally. So I have to be able to distinguish from one T to the other. Because if I were to assume, and I'll just kind of play this out logically, if I were to assume that this T were the same as that T, then what would be, the assumption would be that not only are the paths crossing each other, but they're crossing each other at the same time. Right? So I look at two possible ways of thinking about this. Both of them involve the intersection of two roads. All right, so back to the cars, always cars. So you could have two roads crossing, no problem with that, right? We see that all the time. Yeah. Two cars crossing. Every now and then you see that, right? Yeah, it's terrible to see. I've actually only seen a collision, like a live collision, once. Like, and it wasn't even like from beginning to end. It was more like out of the corner of my eye, I saw something going down, and then as I was turning my head into my field of vision, I could see like the last moment of it happening. But that was really it. So like at this point in time, it's like once in a lifetime for me anyway. So it's completely anecdotal, but bottom line is, you don't need the two cars to collide in order for the roads to intersect, all right? If T here needed to be the same as T there, that would mean, and forget about cars, because that's kind of morbid, as they're paving the roads, like as they're creating the roadways, they would have had to be creating the intersection in such a way that both roads are crossing each other at the same time as the pavement is being laid down, all right? That's not necessarily the case. One road could have been paved first, and then later on the other road could have been put in. All right, bottom line is after the fact, the two roads are there and they cross, all right? Yeah, but it was crazy. I was on the Garden State Parkway, and I was on my way to my wedding rehearsal, and I was in the driver's seat, and I heard my friend in the back seat. He was like, "Whoa, whoa, whoa!" And it just like it was just a weird thing to be yelling out. I was like, "What the hell?" So I turned around and I looked, and as I'm looking, I can see the car as it's slamming into the sidewall of the highway. It's like he described it like they were trying to do a lane change. You know, like you're gonna merge left. You don't realize someone's in your blind spot. So people do that all the time, and swerve back. This person overcompensated and then went right off the road into the guardrail. It was like, oh my God. But I saw it was like, boom. That was pretty insane.
So I hate it when people in the right lane, they don't realize somebody's about to merge. You go on your left side. So I always notice, I kind of like trying to figure out like, hey, I'm gonna probably be at the same. He's gonna probably exit at the same time where I'm on the right side. Let me merge into the left side, give him some room.
Yeah. Yeah, it's just common sense at that
right?
point. Yeah.
I hate that too, because like.
It's not a race. Like I'll let you on. You know, like just I'll do that. Just do that when I'm trying to get on. You know, but people don't think. So accidents happen. But here we're just looking to see will the roads intersect. So what I'm going to do is I am going to put a little subscript here. I'm going to call this T sub 1 as soon as my pen turns back on. T sub 1. And this will be T sub 2. I mean, as long as you distinguish one from the other, you're fine. So maybe you just leave one as T and the other you call T sub 2 or T sub 1. All right, one way or the other, it's okay. So if this is going to play out correctly, what I need is for 3 minus T1.
Could you give me a different letter if you want?
You could, yeah. In this context, absolutely. There are some other problems down the line where we're going to use other letters for other things. So I try to stay away from it. Like I've seen some textbooks, and even I've done this in the past. They've called it like T and S. And I was like, all right, that's fine. S means something else. But the problem in my mind is that, well, there's a lot of problems in my mind. S stands for something else that we're going to cover down the line. I mean, well, we've already covered it. It's arc length. But we're going to learn how to parameterize equations in terms of the arc length of a function, whatever that means. That'll be a fascinating conversation. It's a little mind-bending, a little trippy, but it'll be fun. So if there's going to be an intersection, the first equation has to have some t value that'll get it to a location that corresponds with the location that the other equation gets to based on its own t value. All right, so they both have to get to the same location, but based on their own set of rules. All right, parallel dimensions. There's a portal. All right, so you got Earth 1 and Earth 2. Earth 1's portal is in New York, Earth 2's portal is in London. But they're at the same location in space-time. So if I go through that one portal in New York on Earth 1, it'll bring me out in London on Earth 2, two different locations based on their own sets of rules based on geography and physics. But bottom line is it's the same physical universal location, all right, or multiversal. Although, I don't know if you're all caught up, but Earth 2, no bueno. I don't know how many Arrowverse fans there are, but you have not. All right, so I will not.
I know the gist of it. Multiple
Yeah.
universes that have come together so far.
Yeah, it's happening. It's happening. There's some big goings on. Happened last night in Arrow.
I don't think I've watched since Rachel Gould.
Oh, so season 2 of Arrow, I think. Yeah, season 3.
Yeah.
Season 3, because season 1 was The Undertaking, season 2 was Deathstroke, season 3 was Rage. So, yeah, but you know what? You could pick up with Arrow, you could pick up right now and be good, because this is the final season, there's only 8 episodes, and it's going to set you right up nicely for the crossover, Crisis on Infinite Earths, which comes out at the end of November. 6-part crossover? Maybe Supergirl, Batwoman, Flash, and Arrow. Legends might have one in the back end, but there's going to be a cliffhanger, and then they'll pick it up in the new year.
Arrow was really good for like season 1 and 2. After that, season 3 was alright, and
Then it started taking a dive.
yeah, a really big dive. But the first 2 seasons were strong.
Oh yeah,
They
absolutely.
Really got me, but I didn't like it afterwards.
But you know what? Like the episode last night, they brought you right back to episode 1.
Oh really?
And replayed episode 1, but with a slightly different viewpoint. Like it was pretty solid. So definitely worth the watch, I think. But so my Arrowverse analogies aren't going to always land, but sometimes they will. What we have here is a system of equations with 2 variables, 3 equations, 2 variables. So we're probably going to get some kind of solution. It's just a question of, will we get a unique solution, or will we get infinitely many solutions? Or will we get some kind of contradiction, I guess? But generally, if you have 2 equations, 2 variables, you're looking at some kind of solution coming out of it. Here we got 3 equations, so even better. All right? So you do it algebraically, or we could use the calculator to do the work for us, all right, in the form of a matrix. So what I'm going to do is I'm going to get it so that it's in standard form. So variables on the left and constants on the right. All right, so I'm going to bring the -4t2 over to the left. So I'll have -t1 minus 4t2 equals -2, because I'm just going to subtract the 3. And then 6t1 plus 3t2. That looks like a clean 0 unless I screwed something up. Always possible. All right. And then -2. This is one of those situations where if you had to do it out algebraically, you're not going to spend too much time. You should be fine, because the second equation is nice and convenient. You could solve for T2 pretty easily in terms of T1 or vice versa. But we'll use the calculator. We talked about this in the last unit when we went over some of those word problems with vectors. So it's the same general idea. We're going to make a matrix out of this and use that magical RF technique. All right, so we have to put it in the calculator. So 3 by 3, so we're still good there. You'll get to a point when you'll be so spoiled with the calculator that even things like this will be like, oh man, I gotta put another matrix in. This is annoying. It's taking forever. Because you will have completely lost sight of the fact that this is kind of a pain to do by hand algebraically. And the reason you will have lost sight of it is because I will have never asked you to do it by hand algebraically. So you'll be like, you start forgetting what the amount of work is entailed with the kind of problems that, like you don't have to worry about, right? So you kind of create a new normal where this is even too much for you. You're like, I don't know, oh man, I gotta type another matrix in. But, just in those moments, I don't know, I guess try to imagine a world where you have to do this, which is basically every other Calc 3 linear algebra teacher. So, anyway, doing a quick double check to make sure my data's in correctly. I think I'm all right. Gonna quit it. So then ref, then select matrix A, and we get that. Oh, look at that. Must have done something wrong. Not really. Not the case at all. I'm gonna convert this over to fraction form by hitting math and then option 1. So that's a nicer version of it. Is there a way to get it all on the same screen? No, I don't think so. Well, I guess I could try it this way. No, it's just not going to happen. Although, I could go old school. No, I can't expand it. I was hoping. Bring this back. All right, well, I'll just take the fractional one and paste that in. Well, I don't even have to paste it in because it's actually fairly convenient. So 1, 0, negative 2 sevenths, 0, 1, 4 sevenths, 0, 0, 0. All right. Now, each column would represent a variable. All right. So if I read this across the top, what I'd be looking at is 1 T1 plus 0 T2 is equal to negative 2 sevenths. And then 0 T1 plus 1 T2 would be equal to 4 sevenths. And then the last row, I'll write it, but you'll see very quickly that it's not very meaningful in this context. 0 T1 plus 0 T2 is equal to 0. All right, so if you clean that up a little bit, you get the relevant pieces, which tells me that T1 is equal to negative 2 sevenths. T2 is equal to 4 sevenths. And then the last thing is saying that 0 is equal to 0. All right, cool. 0 is equal to 0. I didn't need that piece of information, but it was given to me because, again, ideally I'd have 2 equations, 2 variables. I had 3 equations, 2 variables. I had 1 extraneous equation, 1 equation that was unnecessary. I could have got the job done with 2 out of the 3 equations. I didn't know which pair I wanted to pick, so I just used them all in the RRF, and the calculator made the choice for me. So that's great news. Now, because we got solutions for T1 and T2, we know that there's going to be an intersection. Now, that's all they asked us to do here. But a question could ask you to determine where they intersect. So we might as well figure that out. So I'll take my, well, it's visible on my screen right now, so I'll take my second equation. So 1 plus 4t2, comma 1 minus 3t2, comma 2 plus 5t2, where t2 is equal to 4/7. All right, and that'll give me the solution vector, which in theory would be the same as whatever I would get if I plugged in T1 for my first equation, which you could use as a good way of checking your work, but not a requirement. If we're just looking for the intersection, what's good for one will be good for the other. So 1 plus 4 times 4/7, ugly decimal, so math bracket, 23/7. One minus 3 times 4/7, and this is just because I want to take a break from thinking. Negative 5/7, and then 2 plus 5 times 4/7. Math bracket, 34/7. All right, so intersection exists. All right, and again, if you wanted to, you could have plugged your T1 value, the negative 2/7, plug that into your T1 set of equations, and you would have gotten the same coordinates, 23/7, negative 5/7, and 34/7. All right, so that's giving us the location of the intersection between the two roads. Now, it's also telling me that time isn't flowing the same way in these two systems, assuming T represents time, right? Because it takes negative 2/7 in order for T1 to hit that intersection, and 4/7 for T2 to hit that intersection, right? So if you're designating 0 as the start of the clock, then, you know, like you're standing there with a stopwatch, and you're just, you know, cars are just driving by. You start the clock, negative 2/7 of a second prior to you starting the clock, this first car was already through the intersection, all right? 4/7 of a second after that, the second car was through the intersection, all right? So, you know, a physical application of this would be, well, is there a collision? I don't know that I'm qualified to answer that, because I don't know how fast, you know, like what kind of intersection are we talking about here? Like if somebody blew a red light going 30 miles an hour at a busy intersection, that kind of thing. Like, would they be through it in like half a second, or would it take longer than that? I don't know. But it would beg the question of, you know, like what are some of the implications of this kind of information? So in order for there to be actually physically a collision, do these two numbers have to be precisely the same? No. If they're very, very close to one another, then that could be good enough to indicate that there is a collision. All right. It may not be a. It could.
Even though the times are not the same.
Yeah.
You consider that to be because they're right close.
Yeah, because maybe one car is taking off the tail bumper of the other car.
So it's like
One's a smart car, one's a fire engine.
Exactly. Oh, smart cars, man.
Smart car driven by a fire truck, I don't think it'd be a smart car.
Yeah, nobody's thinking that's a smart car when that happens. Yeah, I feel like those cars are just designed for like, do you sign a waiver when you buy it? Like, listen, you get in a crash, you're dead. Like, that's it. Yeah. Yeah, you don't have, like, that's it.
There's no cushion.
Yeah, there's nothing. With crumple zone, you are the crumple zone.
Anything bigger than a squirrel, you're done.
Yeah. I mean, a squirrel will be enough to do it. Like, most cars, you hit a deer, you're like, ah, there goes my hood. You hit a squirrel in a smart car, and that's the end of it. Yeah.
The deer doesn't
Totaled.
do you, especially on the hutch. Oh my God, it's we are.
Yeah, exactly. I mean, what shoulder? What shoulder? Who knows? So it's really just a matter of writing the equation of the lines passing through the 2 points, and then just seeing what the relationship is between those two lines. All right. So I'm just doing this. Just bang out some colors right now. Oh. So I'm going to want to find the displacement vector between these 2 points. And you can call it anything you want, but I'm just going to call it P and Q, just to make life a little bit more simple in terms of the notation. So vector P to Q, -2 minus a -4, 0 minus -6, and then -3 minus a 1. Okay, so we're looking at, or this is really a plus, so 2, 6, -4. All right, so for the other one, I'll call it S and T. That's something. Oh wait, I don't know the alphabet. I don't know the alphabet so good. PQ, then RS. I mean, it doesn't matter what you call them, but if I'm, like in my brain, I was like, oh, I'll just use the next 2 letters in the alphabet, and then I felt stupid when I put the wrong letters. So, and then of course I feel the need to always out myself when stuff like that happens. So 5 minus 10, 3 minus 18, and then 14 minus 4. So we're looking at -5, we got -15, and we got, looks like a 10. All right, now we can go back to these relationships, but we're looking for the line through each of these points. So one thing that we might consider doing is writing the equation of the lines in each case. But as it turns out, if you know what the relationship is between the parallel vectors, then you pretty much have what you need. All right. So I'll do it both ways. One way to just show you how you could streamline the process, and the other way would be with the the more visual attributes. All right. So let's say I'm actually going to go through the whole process and write the equation of a line. So I have my starting point. So I would have x, y, z would be equal to -4 plus 2t, -6 plus 6t, and 1 minus 4t. All right, so that would be the equation of the line passing through those 2 points. All right, now you can create a graph. Not on a test, but you could use GeoGebra. You're doing it on your own. You want to see what the relationship is. On a test, you might want to create a table of values and see where things are going. But I'll show you how we're going to streamline it in a second. So the other x, y, z we'd write it, because here's my start, 10 minus 5t, 18 minus 15t, and then the last one is 4 plus 10t. Oop, I could put that away for a second. All right, so those are my two equations of lines. But again, the objective here is to determine if they're parallel to one another. All right, two lines are parallel if their parallel vectors are parallel. All right, so two lines, line starts with an L. All right, that's a lot of parallel in one sentence. Two lines are parallel if their parallel vectors are parallel. So it's like, it kind of almost feels like a fake definition where it's like, they're parallel if they're parallel, but it's really more than that because I'm looking at PQ, vector PQ. I want to know if that is parallel to vector RS. So what I want to know is what the simplified form of PQ would be. So I'm going to factor that. All right. Constant multiple of 2 I can pull out. 1, 3, negative 2. All right. So PQ is itself parallel to another vector. That vector being 1, 3, negative 2 by a scale factor of 2. All right. So if the basis of RS is the same vector, then we have parallel relationships. So I'll do the same thing with the negative 5, negative 15, 10. In that case, it looks like I can pull out a negative 5. If I pull out a negative 5, I'm going to have 1, 3, negative 2. So RS, a PQ and RS are parallel to 1, 3, negative 2. Therefore, they are parallel to each other. But I still want to answer the question. It says it's a line through those points. So my final conclusion, the two lines are parallel. I didn't name them, so I'm just going to call them the two lines. All right. If you wanted to, you could call the first one line L. Typically, we start off with a lowercase script L for a line, to represent a line, and then that's the beginning part of the alphabet from there. So the next one would be M, and then N, and so on. All right. So for points, we start off with point P, and then we follow the alphabet from there. For variables, we start off with X, follow the alphabet from there. Constants, we start off with A, we follow the alphabet from there. All right. So, you know, there's just naming conventions, but they're not, you know, hard, fast rules. So I wrote a lot of extra stuff for note-taking purposes, but really, you would just need these vectors and these calculations, and then just a statement of the final relationship between the two. All right. So it's really not it's not as lengthy of a process as I just made it seem. All right. So there's that. Okay. So distance between a point and a line. All right. So we just found the intersection between a point and a line. So now we have the distance between the point and the line. So definition of this is really, I mean, it's fairly straightforward. It's the cross product between, we're calling it PM. If we look at the diagram, PM is the distance that we're actually looking for, and vector V, all right, over the magnitude of V. So I'll get into the derivation, I think, next time, because it's going to kind of bring things to a screeching halt at this point. But in terms of the actual process, it's not terrible. We just need to come up with the relevant vectors. When it says find the distance between the point 0, 3, 6, and the line with parametric equations, 1 minus t, 1 plus 2t, and then 5 plus 3t, we're looking at 1, negative 1, I was looking at the wrong thing, 2, 3 as my parallel vector. X sub O, Y sub O, Z sub O. I'm just kind of working backwards from the parametric form. The coordinate, which we're calling point P, is going to be equal to, that's the 115. Now my pen doesn't want to cooperate. All right, so that's all information I'm pulling from the parametric equations. Okay. This point here is 0, 3, 6. That's the point M based off of this diagram. That's the point in space. All right, so I need the displacement vector P to M, which once you have everything labeled up isn't bad. So we're pinning it at P. We're looking at negative 1, oh, I'll write it out, 0 minus 1, 3 minus 1, 6 minus 5, which gives me negative 1, 2, 1. All right, so that's my P to M. We need to cross that with V and then use that and divide that by its the vector magnitude. All right, so the magnitude of the cross product, there's a shortcut formula for that, but we talked about it last time. It's kind of like 6 of one, half a dozen the other, because like in terms of the preference, it could be fine. I would determine whether or not it's valid, or not valid, valid's not the right word, a good idea to use the shortcut rule. I would make that determination based on whether or not I was given an angle. Because we were talking about it last time, it's kind of more trouble than it's worth to use the shortcut rule, which ends up not being much of a shortcut if you have to solve for the angle to begin with. All right, if you have to use that cosine rule, u dot v over the magnitudes multiplied, to figure out what theta is, to then plug it into your magnitude of u times v times the sine of theta, it's like, I feel like I'm doing way too much work for something like that. So in this context, I think it ends up being easier to just find the cross product of PM and vector V, and then find the magnitude after the fact. All right, so IJK, PM is negative 1, 2, 1. V is negative 1, 2, 3. It's up to you if you want to get the framework out the way I'm doing it here. I find that people who struggle with the concept of the cross product, they don't struggle with the mechanics of it. They just forget that the J term is supposed to be negative. And so a little reminder to yourself might not be the worst idea in the world. Right, so for the I, I'm gonna just, I know I'm not really covering anything up here, but pretend I am. Diagonal down minus diagonal up for the JK. So 6 minus 2 is gonna be a 4. Then for the J, so diagonal down is going to be -3. Diagonal up is going to be -1. But we're looking at diagonal down minus up, diagonal up. So -3 minus a -1, so -2. All right. So -2 is going to be the result, but we already have a negative built in, so +2. Actually, I'm going to leave that showing a little purple there to show that I changed it from negative to positive. And then K, diagonal down -2, diagonal up -2, -2 minus -2, so -2 plus 2, so that zeroes out. All right. So the magnitude of PM by V is going to be the squared values added together. You don't have to write 0 squared if you don't want, but just for note-taking purposes, I'll throw it in there. Rad 20. We also need the magnitude of vector V. All right, so that's this guy here, vector V. So magnitude of V, -1 squared plus 2 squared plus 3 squared. I'll put it below. So the square root, we got 1 plus 4 plus 9. So it looks like the square root of 14. All right, and so the distance between these 2 points is just going to be the quotient. All right, so the distance is going to be the square root of 20 over the square root of 14. And you can simplify if you want. I mean, there's not much to simplify in this case. Divide top and bottom by 2, so 10/7. But in terms of a decimal value, I don't think there's any more benefit to having a decimal than there is having a fractional value. All right, but that's, I'm kind of debating now. Maybe I will get into the yeah, I'll just give you the short version. It's not really too much of a proof as much as it is a demonstration. So if I go to my diagram there, and I just realized I cut off some of this stuff. If I go to my diagram and create a rectangle out of the relevant pieces, so if I were to find the magnitude of the cross product, that's equal to the area of that. In this diagram, it actually ends up being a rectangle, but it's the area of the parallelogram. All right, so PM crossed with V, so the magnitude of V, so here's V itself, this piece. Because all of our vectors are displacement vectors, they're going to be pinned at the origin. All right, so area of a parallelogram is base times height. All right, so I'm saying that PM crossed with V would be equal to the base times the height. Now, the base here can be thought of as the magnitude of vector V. The height can be thought of as the magnitude of, well, we're calling it D, but it's really the magnitude of PM. All right, so I'll just write magnitude of PM. All right, so really it's just going to be magnitude of V multiplied by the magnitude of PM. But the magnitude of PM itself is the distance that we're looking for. So distance multiplied by the magnitude of V would be equal to the cross product's magnitude. And so if I just divide both sides by the magnitude of V, the scalar value, the magnitude of V, I get the resulting value for distance. Stay away from purple there, I guess. And so that's where the formula comes from. And it's kind of a cool origin story, but it's kind of interesting to think that when we start talking about multivariables situations, that there's actually going to be an even cooler way to figure out the distance between a point in a line in space, a point in any curve. And it's going to involve partial derivatives, so exciting times ahead. All right, but we're still in the foundational part of things because we just learned how to define a line in 3 dimensions. So, fun fact, by learning how to define a line in 3 dimensions, we've actually learned how to define a line in 4 dimensions, 5 dimensions, 20 dimensions, doesn't matter. Because we just basically discovered on the previous page anyway, that we're gonna define them parametrically. So parametrically is just telling us that however many dimensions you are, you need to have a component within your vector value function, to represent each one of those dimensions. All right, so if I'm working in 4-dimensional space, I have to have a component for x. Well, once I get out of x, y, z, if I go into 4 dimensions, instead of saying x, y, z, I'll say x sub 1, y sub 1, z sub 1. I keep doing that. X sub 1, x sub 2, x sub 3. When I get into 4-dimensional space, I'll just add an x sub 4, 5th dimensional x sub 5. It makes it a little easier because if I go to 20th dimensions, then it would be x of 20, and then I could use some knowledges from sequences and series from Calc 2 to be able to streamline the process a little bit. But if I have, let's say, 6 dimensions, all that's telling me is that I have to have 6 components to my vector, all right? But it's still gonna have the same structure. I would still need to have a parallel vector. I would still need to have a starting point. All right, so you're like, well, what would a vector look like in 6-dimensional space? Well, it's not really so much of a question of what the vector would look like. It's more so, what would the coordinate axes look like? You know, because at some point you start running out of ways to represent different dimensions. You'd have length, width, height, but then maybe you would define the width as being kind of an angular rotation away from the x-axis and call that the y-axis, and then another movement, the z-axis, and so on. Right? So we'll explore all that stuff down the line and how you could actually geometrically make sense of higher order dimensions. Right? But for now, basically, since we've covered everything that there is to cover about lines, let's talk about the next dimensional representation of a geometric figure in coordinate geometry, and that would be a plane, right? So what a line is to 2 dimensions is what a plane would be to 3 dimensions. So lines can be parallel in 2 dimensions, or they can intersect. Those are your only 2 possibilities. If they're not parallel, they must intersect, right? In 3 dimensions, lines can be parallel, they can intersect, or maybe they could be neither. All right, these two lines are neither parallel nor do they intersect. They're skew lines. All right, but planes in 3 dimensions, possibilities, they're either going to be parallel. This is even parallel. All right, parallel. If they're a restricted domain, maybe it's like a strip of a rectangle in one direction, a strip of a rectangle in another direction, but they are parallel because they're equidistant from one another in the relevant locations. Or they're going to intersect. All right, so if the two planes are not perfectly parallel to one another, at some point they're going to intersect. All right. So what happens for lines in 2 dimensions is what's going to happen for planes in 3 dimensions. There's no way for them to be askew, right? But if you take 2 planes and put them in the 4th dimension, now you could have planes that are either parallel, intersecting, or completely missing one another, all right? Because we're introducing an additional dimension, all right? More on that later. But for now, all we're going to do is explore how on earth, how do you write the equation of a plane, and then how do you graph it, right? So what we look for here is something called a normal vector. All right, a normal vector is a vector that we know is orthogonal to the plane. All right, so it has to form a 90-degree angle with the plane. And the conclusions you draw about your normal vector will also dictate the same conclusions for the planes themselves. All right, so now orthogonality is based on the dot product. So if 2 elements, 2 things are orthogonal to one another, their dot product is equal to 0. So I'm defining a vector that's living in the plane as PQ. So this is a vector that's on the plane. And the other vector, the one that's defining the nature of the plane, is the one that has to be normal to it. Normal vector. All right. They have to come together to form a right angle. So they have to be orthogonal to one another. So the normal vector we define as ABC. I'm going to go red for that one. PQ is the displacement vector between x sub o, y sub o, z sub o, and x, y, z. So that's going to just be x minus x sub o y minus y sub o, z minus z sub o. That result needs to be equal to 0. That is the definition of a plane. All right, but I don't want to write it like that. That's ugly. Let's clean it up. Let's find the actual dot product between these 2 vectors. So I'm going to run the A through, then I'm going to run the B through. So just distribute it through its corresponding parts. And I'm going to need a fresh color here. Oh, I'll just use, well, I already used black. I'll just jazz it up here. There's nothing to do but get a little spicy. Custom color palette. I need like a nice green. Let's see, is that visible? Yeah, reasonably visible. All right, so we're looking at AX minus AX sub O plus BY minus BY sub O plus CZ minus CZ sub O equals 0. I'm going to clean things up because ax sub o, by sub o, and cz sub o, those are all going to be scalar values. The variable stuff I want to keep on the left, so we're going to have ax plus by plus cz, and then everything else is going to go to the right. So ax sub o plus by sub o plus cz sub o. So what we've ended up kind of deciding upon, and I say we as if I had any say in this, decided to let the whole right-hand side equal some constant d. Just some made-up value. Not really. Where d is equal to the dot product between n and p. Or vector p. Kind of streamlines it a little bit, makes it a little bit cleaner. It's kind of like conic sections. Like when you're graphing an ellipse or something like that, it's x squared over a squared and y squared over b squared. It's like, well, a and b mean something. As long as you know what they mean, you know how to graph the ellipse.
Wait, what does D mean here?
D is going to be the dot product between the normal vector and the vector going to p. So we're just dotting these two values. Okay? And that's really what this is the result of. So if I undot this, this is what the expression that would be, that represents that. Not so good with the grammar, but hopefully I got that idea across.
Is P the same as P?
No, just the p. Because p is x sub o, y sub o, z sub o. So if I were to create a vector to point p from 0, it would be vector p is x sub o, y sub o, z sub o, just with the triangular brackets on it.
It's not the unit vector. P is not the unit vector.
No.
It's just the base vector.
Just some displacement vector from 0.
Vector from,
Yeah.
it's what they call the base vector, like something like the base that's going.
Yeah, that's another name for it. Yeah. All right, so in number 6, it's asking us to find the equation of a plane connecting or containing the points and perpendicular to the given vector. So it's actually very straightforward. So all we're going to do is just kind of label this up a little bit. So if it's going to be perpendicular to the vector of 3, 3, 6, then that's making n 3, 3, 6. If it's going through this point 2, 2, 1, that's going to be my point P 2, 2, 1. So I just need vector P, which is going to be also 2, 2, 1. Then I need D, which is the dot product of N and P. Which is 18. So that gives you the right-hand side of your equation, which is really the only challenging part of it, because the normal vector is made up of your A, B, and C values. Which serve as the coefficients of x, y, z on the left-hand side. So I'm looking at 3x plus 3y plus 6z is equal to 18. That's the equation of the plane. Now I just want to graph that. Now the reality is, if I'm graphing a plane, the correct way to do it would be to take your piece of paper, lay it flat on the desk, take the side, you know, like when you're shading using a pencil, you know, take that side of the pencil, start in the upper left-hand corner of the paper, and start shading. And then after about 20 minutes or so, you will have shaded the entire piece of paper. All right, shaded from upper left all the way to the lower right, hitting every square inch of the surface of the piece of paper, because planes are infinite. All right, length, width. If you were to properly graph a plane, it would cover your entire sheet of paper. All right, so that's not a good way to do it. We don't want to do it that way. What we're going to do is graph a triangular cross section of the plane consistent with the x, y, and z intercepts. All right, so that's all we're going to do. We're going to find the x, y, z intercepts, and then we're going to connect them, and then we're going to shade that portion of it in, which is actually not hard at all. So x intercept, you get that by letting y and z equal 0. 3x plus 3 times 0 plus 6 times 0 is equal to 18. You wouldn't have to show that work. You could just write 3x is equal to 18, getting x equal to 6. For the y-intercept, you let x and z equal 0. Leave y variable. And same idea as what you would do if you were graphing x and y intercepts in the two-dimensional system. You know, you just let the other variable equal 0. Here you just have a couple of other variables. All right, so the z-intercept, let x and y equal 0. And you get your z-intercept. So you just have to plot those. Now the things that make plotting on a coordinate, on a three-dimensional system challenging won't really play a role here because we're living on the axes. All right, so 6 steps, 2, 3, 4, 5, 6 in the direction of x, 6 steps in the direction of y, and 3 steps in the direction of z. Connect them. I'll use my line draw tool because, you know. Oh, that sucked. Not any better. That one I'm going to have to freehand. Okay, pretty bad, but whatever. And then just shade that bad boy in. And this is a triangular cross section of your plane. Really, all we needed to do is give us a sense of the orientation of the plane as it relates to the x, y, and z axis. Yeah, so it's really not bad when you think of it that way. All right, the big challenge is actually coming up with the equation of the plane to begin with. But that's not too terrible. Here, let me just point it out to you here. So this is what I'm really addressing here. We're talking about the dot product between the point on the plane in vector form and the normal vector. All right. So whatever point you know is definitely on the plane that's going through that normal, or the normal vector is going through it, that's what you want to dot against that normal vector. All right, so page 36, I believe, number 7, it's 2 pages later, so whatever page it is. So find the equation of a plane containing the points, this, that, and the other thing. So what I'm gonna need are vectors. So let me plot some vectors here, or draw some vectors, I meant to say. Yeah, it's up to you if you want to name them. Most people can get through the whole process without ever naming a point. You keep it organized in your own way, it's perfectly fine. But just so you know what the hell I'm talking about, I'm gonna name them. So I'll PQ, vector PQ, and vector PR. All right. So, and I'm not going to look at these points up here because that's going to make things confusing because then I have to relabel it because Q, based on the distribution here, Q is the first one, R is the second. It would be annoying. So I'm just going to look at the picture now. Q minus P, R minus P. Maybe we're just getting it from both angles here. Let me do this.
So what are your three, these are your three, like, what are your three types? So,
The people across the hall aren't quiet either. So, for P to Q, 3 minus negative 1, so 4. 1 minus negative 2, so 3. 4 minus negative 3, so 7. Then we have 2 minus negative 1, so 3. 7 minus negative 2, so 9. 1 minus negative 3, so 4. All right, so that's our PQ and PR. Now, in order to write the equation of a plane, well, we need a couple of pieces of information. We need a point on the plane, but we also need the normal vector. All right, so we know that there is a vector that is perpendicular to these two. I'll just draw a rough estimate of what it might look like. So for example here, so you have this entire plane, well these two vectors living in the plane, and this is going to be perpendicular to that, all right, to that surface. So we want to find that normal vector. The way we do that is by computing the cross product. So I need PQ crossed against PR. All right, so we get a little bit of I'll just do it below it. We have a little bit of computation ahead of us. So, and again, I made this suggestion. It's up to you if you want to follow it, but I like to get my I, J, and K's in there, and then pop my coefficients in there later. And it's really not because I'm worried that I'm going to forget the I, J, and K. It's that I'm worried that I'm going to forget that the J is the negative. All right, and so little things like that help you to avoid making careless errors. All right, so use a highlighter here. We're going to go, so I is going to be this set of values, because basically everything except for the I column. So downward diagonal gives us a product of 12. Upward diagonal gives us a product of 63. So we're looking at 12 minus 63, which is what, negative 51? Come on, get out of there. Negative 50. Poor quality negative symbol. I'm just going to fix that real quick. Poor quality 5. There we go. Back in the game. All right. So now I'm looking at the J. So that's these two. So everything but the J. downward diagonal is 16, upward diagonal is 21, so 16 minus 21 is negative 5. So we're looking at negative negative 5, so plus 5. And then the last one, I against j, or I and j, ignore the k. All right, so downward diagonal 36, upward diagonal 9, so 36 minus 9, 27. All right, so this is the normal vector. So n in component form, negative 51, 5, 27. All right, so we have the left side of the plane. Now we just need the right-hand side. All right, so if you, I mean, you could flip back in your packet, but you could also kind of think it through. If on the right-hand side, really it's just the normal vector and the point that you want to have on the plane. All right, so actually let me do it a little. In this case, that ends up being this point. So that's this guy right here. All right, so I'm going to dot n against p. All right, so that's going to be the same as saying negative 51, 5, 27, dotted against negative 1, negative 2, negative 3. All right, so we're looking at 51 minus 10 minus 81. (27 times 3 is 81, right? Yeah. All right, so, well, 51 minus 81 is negative 30. Negative 30 minus 10 is negative 40. All right, so this is our D value. And remember, the general form is AX plus BY plus CZ is equal to D. The normal vector, do that in a different color, your normal vector is ABC. So we have everything. It's gonna be ugly, but it'll do it. Negative 51x plus 5y plus 27z equals negative 40. It might look a little cleaner if you negate everything. We could say positive 51x minus 5y minus 27z is equal to positive 40. Either one is fine. It's just one of them just felt a little cleaner, and there's sometimes a little benefit to doing that, but in this case it wouldn't make a difference either way. All right, so we'll check that on GeoGebra in a minute. But the process is, I mean, that is the process. You gotta do the cross product. There's no way around it. I mean, that's not true. There are ways around it, but that's the most convenient way of handling it. All right. So intersection of planes, and this is something that it's pretty logical when you think about it. In order for two planes to intersect, their normal vectors have to intersect. Right? So, if we're looking for the equation of the plane containing the point that's parallel to this,
Here I can't really do too much. I can't really do too much because again I have to worry about the D later on. But this part I can clean up. This one I know is 0, right? 0 divided by 1 is.
would have liked to have an example immediately that involves whatever. Maybe I did it last class. I don't remember. So, but yeah. So if two planes are going to intersect, the normal vectors have to intersect. If two planes are going to be parallel, then their normal vectors have to be parallel. All right, so for number 8, when it says find the equation of a plane containing this point that's parallel to the plane, all I'm going to do is pull out this normal vector. Normal vector is 2, 1, 1. This is going to be point P, but I want vector P, which is just basically the same thing with the triangular fencing. All right. So if I want to write the plane equation, I already know what the left-hand side is going to be. I need to figure out the right-hand side, which is the dot product of N and P. So 6 plus 1 plus 4, result is going to be 11. All right, so my parallel plane is going to be 2x plus y plus z is equal to the right-hand side, which is 11, because that's my d value. All right, so intersection of the planes. All right, so this is the example I was hemming and hawing about on the previous page. Like, oh, I should have had an example of intersection of planes. Well, here it is. So 2x plus y plus z equals 1. So I'm going to just write the coefficients. 2, 1, 1, 1. 3x minus 5y plus z equals 4. So I'm going to just write the coefficients. 3, negative 5, 1, 4. All right, and that's because it's in the proper standard form. All right, ax plus by plus cz equals d. All right, all the variables on the left, constants on the right, that's how we want it. So this is going to go into the calculator, and we're going to put it in reduced row echelon form. So it's going to simplify it for us. We're going to let the calculator do the heavy lifting. Actually, we're going to let it do all the lifting. That's the whole point. And even in that context, I mean, really, if you think about it, it was like, that was pretty much flat out given to us. All right. So into the matrix editor, go to edit. I just manipulate matrix A over and over again. Every now and then I have to perform operations on multiple matrices, but if it's just a standalone matrix, I just overwrite the previous one. So it's a 2 by 4, 2, 1, 1, 1, 3, negative 5, 1, and a 4. All right. Now the intersection of planes, if they do intersect, should be a line. Right? Lines are represented in 3 space in parametric form. So we're on the lookout for an x equals, y equals, and z equals. All right, so I'm going to quit out of here. Math. Sorry, wrong course. I was thinking of probability. I said math probability option 2, 3, or 4 like 17 times today, so it's like ingrained in my mind. Matrix, so second inverse math, so that's part of it. Reduce row echelon form, and we're going to select matrix A. And we get this glorious mess. Enjoy writing those decimals down. No, you just hit math, and then select frac. Math, enter, enter. Calculator will convert it over to fraction form for you. All right, so we're looking at, I mean, they're not the nicest fractions in the world, but it's still better than writing those hairy decimals down. Pen turned off. Pen's back on. So the number crunching is never going to be a hard part of this process. It's knowing what these numbers mean. Even that's not hard. It's just that's the thing that you need to do. All right. So I have a tendency to kind of over-explain when it comes to this, and it's no different from when I'm writing a solution. So I would look at this and say, well, originally it was 2x plus 1y plus 1z equals 1. Now it's 1x plus 0y plus 6 over 13z is equal to 9/13. Then the second one, I'll leave a little space because I'm going to clean that up a little bit. So 0x plus 1y plus 1/13 z is equal to negative 5/13. All right. Now, in each of these cases, there is a variable that you can solve for. So solve for the variable that it makes sense to solve for. All right. So in the case of the first equation, the 0y that's gone. It makes sense to solve for x here because it's a coefficient of 1. So I'm going to subtract off the 6/13 z. So that's going to be x equals 9/13 minus 6 over 13z. And then in the second case, it's going to be y equals negative 5/13 minus 1 over 13z. The only thing that we have, it's not really an issue, it's just you look at it and say, well, I don't see a z. I mean, I see the z as being part of other equations, but what is z equal to? It's not like it's not equal to anything, you know, like it's just not addressed based off of this, all right? So what we get from this is that z is a free variable, all right? Meaning that z could be anything, all right? Because x and y are dependent on z, but we're not saying anything about any restrictions related to z. Z is not dependent on anything. So z is its own person. Z is independent. So z is equal to z. All right. So now it's just a matter of actually stating this in a reasonable way, right? And that's because parametric equations are usually defined in terms of t. So I don't see a t here, but what I can do is define a t to replace z in some capacity. Now you have complete license here because what this is saying is that z can be anything. All right, z can be literally anything. All right, so I could let z equal t. But then I start looking at this and I say, well, maybe I want to make it a little nicer. Maybe I want to get a little greedy. Maybe I want to let it be equal to 13t because then it'll cancel out these denominators. But in the end, it doesn't really matter. All right, so let z equal some unknown value t. So we'll define it in terms of t. And so we would conclude that x is equal to 9 over 13, poor quality 13, hold on. Coming back, there it is. Minus 6 over 13t. Y is equal to negative 5/13 minus 1/13 t. And z would be equal to t. It doesn't have to be t. It could be anything. You let it be equal to r. You could leave it in terms of z if you want. But I changed it to t because every other time we wrote a parametric equation, it was in terms of t. So for consistency, that's what I'm going to do. But you can see you got a lot of wiggle room. And then if it's a contextual situation, you might even let z be equal to a number. You know, if you have a cause to do that, there's nothing wrong with that either. All right. All right, so this concept, distance between a point and a plane, very important concept. And in fact, we're going to come back to this in the next unit when we get into the multivariable stuff. Because next unit is like, it's free. Because then we start taking like all the calculus stuff and merging it together with all this stuff. It's like, if you like math, you're gonna like the next unit. I mean, that's just all there is to it, right? But you see a problem like this where I say, what is the distance between a point and a plane? It seems like a very bland problem. You know, there's no context whatsoever. In the next unit, I'm going to show you a completely different approach for solving a problem like this, to the point where you'll be like, which way do we have to do it? And my answer would be any way you want. It doesn't matter. It's just going to be another skill. But at this point, since we know vectors, we'll use a vector approach, right? So distance between a point and a plane that contains another point is going to be defined by this relationship. The dot product of, well, QP, which is just a vector between the point on the plane and the point in space, and the normal vector divided by the magnitude of the normal vector. All right. Now you start getting into, okay, well, why? Just why? Yeah, that's one hell of a formula to take on faith, I would think. All right. So we have little things that we could rely upon, and one of those things is this component aspect. We talked about this a while ago. So the component of QP acting in the direction of n. All right, that's really all this is coming down to, because n is the normal vector to the plane, but if I have some point flying around there in space, so that point P, that's the thing that I'm looking to find the distance between itself and the plane. That point on the plane could be anywhere. All right, so there's no guarantee that the distance between 2 points in general, like if we use the distance formula, you might say that. Like, why not use the distance formula? I don't know that the shortest distance between that point and the plane is going to be this point Q. I mean, it's based on this diagram, it's definitely not, right? So any point on a plane, I can figure that out just by looking at the plane. I just got to come up with an ordered triple that satisfies this. So for example, 1, 1, 2. X equals 1, y equals 1, z equals 2. Or 4, 0, 0. Or 0, 0, 4. Or 0, 4, 0. Right? There's infinitely many possibilities that could satisfy this. All right? How do I know that the point I select is going to be the one that's the closest one to the point that's flying around in space? I don't. All right? So that's the issue. All right? So what we do is we actually find the vector going from the point that we choose, which is QP, all right? Because I'm arbitrarily selecting a point, all right? So I almost fell. I'm arbitrarily selecting a point. So I'm choosing this point. Now we're hoping for R. We're hoping to get that point R, but there's no reason to think that we're ever going to be able to stumble upon a value like that unless you know that the plane is horizontal and the point, the plane is horizontal or vertical or something like that, and the point is just some known distance away from that plane. That's a different story. But we're choosing this point, and then we're going to compute the vector QP. So I'll play around with the example first, and then I'll get into the proof afterwards. All right. So this point Q, it can be literally anything that satisfies this equation. So my first instinct was 1, 1, 2, so that's what I'm going to go with. All right. So any point that satisfies the equation. All right, so you can, if you wanted to, when I'm going through this example, maybe you choose something else. Maybe you choose 6, -1, -1. If you carry out the process the same way I do, you'll come up with the same answer. It does not matter what point you choose. All right. So then what we do is we find vector QP. Which is going to be 3 minus 1, which is 2. 1 minus 1, which is 0. 4 minus 2 is 2. All right. So theoretically, what's happening is, again, we can't figure out a distance that we don't know the two endpoints to. I know where point P is. I have no idea where point R is. But what I can do is figure out the component of QP acting in the direction of the normal vector n. And if I do that, then what that'll do is it'll give me a vector's distance that is parallel to the one that I'm looking for. All right? So these two line segments, and let me just kind of pull it in a little bit. Green is what I want. These two lines are going to be equivalent. All right. So the component acting in the direction of n, a vector QP, that magnitude is going to be equal to the magnitude of RP. All right, so if I find one, I find the other. And so all we're really doing, just using the notation of this diagram, we're just going back to the derivation of a component from one vector acting in the direction of the other, right? So the whole adjacent over hypotenuse business and all that good stuff, all right? So if you just think, it's really just the same concept as what is the definition of a component, projection component. It expands from this form to that form, and then there you have it, right? But the key is knowing that these two distances have to be the same, all right? And that's really all there is to it. So once you have that, it's just a matter of carrying out the process. So n, the normal vector, is equal to 1, 1, 1. Its magnitude is equal to the square root of 3. If I can draw a square root. And so the distance, well, actually, let me do the dot product first. So QP dotted with n is going to be 2 plus 0 plus 2, which is 4. And so the distance is going to be the absolute value of those two numbers divided. So 4 over the square root of 3. There were no negatives, so I don't have to worry about the absolute. All right, so that's actually the distance between the point and the plane. All right, but this idea of congruence between the two opposite sides of this parallelogram, that's what drives the whole thing, because that allows me to select a point anywhere on the plane, knowing that whatever this distance is in space has to be equivalent to that one, which is ultimately the one I'm looking for. All right. So for some of us, it's just a process. Like, follow the steps. But if you can kind of start to internalize why things work the way they do, it makes it a little easier.
What is this?
You got the n from just the x, y, and z equals 4.
Correct.
What is this? Next to dot n equals 2 plus 0.
2 plus 0 plus 2 equals 4.
No, but what's the thing before the dot n?
QP.
Oh.
Vector QP.
For the component n, QP equals, should it be PR or RP?
Oh, did I just write the same letter twice? Reading railroad. Jeez Louise. Yeah, it's a Monday mistake. Problem is, I make those mistakes every other day of the week too. But yeah. I almost did it again right there. I always want to tail it. All right, and so number 11 is like, all right, it's the same idea, but you're like, oh, we don't have a point. Yeah, they didn't give us that free point like in number 10. So pick it. We're going to do the same thing, but I just need a point that's going to satisfy this equation. So let's say 0, 0, 6. Zeros are nice numbers. You really can't go wrong with them. All right, so they just need a point that you know is going to satisfy the equation. So that's what we're going to call point P, because if I find the distance between a point on one plane and the other plane, so not a point on one plane and a point on the other plane, a point on one plane and the other plane itself, then I will have found the distance between the two planes. All right, because if I take a different approach, it's dangerous. I've seen people say, okay, well, I'll find a point on the first plane, find a point on the second plane, and I'll use the distance formula to find the distance between the two of them. There's no guarantee that one isn't like all the way that way and the other isn't all the way that way. It might not be the shortest distance between the planes. We need the shortest distance. All right, so the normal vector, you could pull that out of this, because this is the plane that we're working with. Normal vector is going to be 4, -6, 2. All right. I also need a point on the second plane. It doesn't have to be anything in particular, but I do need that point Q, something that would satisfy the second plane. Now, you can go with zeros. Zeros are a wonderful number. So I can do 0 for x, 0 for y, and then that would force z to be 4. You could do 1, 1, and then 1, 1, 1. Right? Oh no, it's got to go to 8. So 1, 1. I would need 10, 1, 1, 5, I think. Something like that. So then QP, but regardless, it doesn't matter what you choose as long as it satisfies the equation. So QP, we're looking at 0, 0, 2. We have our normal vector, so I need the dot product of Q, P, and N. So 0 plus 0, another benefit of having lots of zeros, plus 4. It's going to be equal to 4. Magnitude of N. So 16 plus 36 plus 4 is adding the squared values together. Poor quality plus sign. Let me just square that away real quick. So root 56. So my distance is going to be the dot product, which is 4, over the magnitude, which is root 56. And that's where we leave it, because anything, I mean, you could simplify if you want or try to, but you're not going to get any extra credit for it, so why bother? I mean, decimal values are fine too, but then you got to get into rounding and the potential for rounding it incorrectly, so just leave it like this. I've mentioned this before, but I don't think I can say it often enough. I'm not overly concerned with simplifying fractions and things like that. The only thing that I need you to do is the obvious cases. So like, don't ever leave it as like 20 over 2. All right, that you make a 10. But 4 over root 56, you can leave that as is. all right? Because I've had people, they'll leave a final answer as 100 over 50, and I'll take off half a point, and they'll wonder why. I'd be like, because you left it as 100 over 50. Well, you said we didn't have to simplify. Yeah, but, come on. Yeah, anything is a whole number. Come on, just throw it down there. Now, it is possible that you might look at something like 343 over the square root of 27 or something like that. I don't even know if I'm making up reasonable numbers. I'll say 729 over the square root of 27. That I know works. You can simplify that down, but there's no point, right? So just leave it. Anyway, I'm trying to. It's actually fairly quick. It's that concept that I've been alluding to, I've been teasing for a while. It's called the vector value function. I've actually been working with it fairly frequently. It's just we haven't always had to call it a vector value function. In fact, this time in this particular semester, I've kind of made it more of a point to use that term earlier in the course, just to kind of familiarize everybody with that vocabulary. Vector valued function is really just saying that you have a function that is incorporated into a vector in some capacity. So what does that mean? Well, anytime you have a function, you have everything that goes along with it, right? So you spend about 3 years maybe. I mean, if you're thinking in terms of college level type math, whether you did it in high school or college, or you kind of spread it out. But essentially like 6 courses, maybe 5 courses, 4 courses, depending if you skipped, but minimum 4 courses related to function mathematics. All right, so you're talking like your algebra, basic algebra, algebra 2, pre-calc, calc 1, calc 2. Maybe you did some other courses in there, you know, like if you took differential equations or something like that. Right? These are all things that come into play. Maybe you took a science class that dealt with some functions also. Right? If you took a science class, you dealt with functions. You know, like anything that involved computation, because input-output is all function. All right? Getting an output for a given set of inputs, that is the definition of a function. All right? So everything that goes along with functions is going to come into play here, except we're going to look at it from, you know, through a vector lens. All right? So if you look at it here, you have an input. We're calling it a real number t. But the output is going to be f of t, g of t, h of t. All right? Okay, so maybe you don't like that. How about x of t, y of t, z of t? All right? It doesn't matter what you call it, it's all the same. You can use IJK notation, but bottom line is you're dealing with a vector that's made up of variable components. That could be as easy or as difficult as the vectors, or as the function itself. All right? So as the components that make up that vector. Right? If you're dealing with something that's got some crazy functions embedded into it, then it could be a little funky. But odds are it's not going to be something outside of your area of expertise. Right? So basically all this whole page is saying is that I can take any function, whether it's a parabola, a line, any kind of line, and represent it as a vector value function. Right? I could represent it as a vector containing variable quantities, right? Which makes it very flexible, right? Because if I'm telling you that we can take vectors and expand it into 3 dimensions, 4 dimensions, 10 dimensions, what that's telling us is that I can take any function and expand it into 3 dimensions, 4 dimensions, 10 dimensions. I can take a parabola and put it into 5 space, all right? So as a parabola, not as a surface. All right, just based on the concept of a vector value function. So pretty interesting segue into the next page that you're already convinced about, so I'll just move on. Of course. All right. But really all we're going to talk about tonight is how to graph these things. Basic. All right. For number 1, this is almost precisely what we did in the first unit. except it looks like it's not even remotely like what we did in the first unit. This is like the first lesson of the first unit. When I gave you x equals this, y equals that, let's put it in our calculator, get a table of values. It's the same thing, all right? So there's no reason to be intimidated. You've seen this before, all right? This is saying that x is equal to 4t minus 1, all right? And y is equal to 2t plus 5. This is a set of parametric equations. In 2 space. I'll write it this way. Real space dimension 2, but it just means 2D. So how would you graph that? It's really not difficult. All you're going to do is make a table of values, an exhaustive table of values, complete with many, many numerical computations, hours of work. Not at all. Yeah, it's going to be a line. What do you need to draw a line? 2 points and a ruler. That's it, in 2 dimensions anyway. So I just need a couple of values. But the form that it's going to take is a little bit different, so I'm just going to kind of walk you through that really quickly. All right. So the question would be, well, what values of t make sense? My answer to that is, well, I guess look at the graph. I see an origin. All right, so I'm guessing that the x and y values are going to have to hit 0 at some point. All right, so I would take a look at my t value and see if there's some extreme values of t that would have to come into play here in order to make this value equal to 0. Well, in order to be 0, t has to be a quarter. All right, so I don't think t needs to be very extreme. So I can keep t pretty low. I can keep it around 0, maybe like -3, -2. Maybe I'll just do -2. Then I'll do a 0, and I'll do a +2. Really, I only need 2 points. Whenever I graph a line, I always just throw the third point in there in case I screwed up a calculation on one of the first two. All right, because if it's going to be a line, the third one will be the tiebreaker. All right, if I get something that doesn't end up being collinear, then I know I screwed something up. All right, so if I plug in the t of -2 here, I'm going to get -8 minus 1 is -9. Plug in a -2 for the other one. -4 plus 5 is a +1. All right, that's the definition of stealing my own thunder. So I'm looking at a vector -9, 1. All right, so this is going to be a vector, and this is the part that's kind of a little bit different from the way you would draw a line. All right, that's definitely a little bit different. I'm going to have to freehand that. I'm going to have to zoom in and freehand it. All right, imagine that is a straight line vector. It's glorious. Yeah, it looks terrible. All right, so for the next value, 0 is going to be easy enough, -1, 5. That was super easy, barely an inconvenience. All right, so that's going to be my second vector. Now my third vector, I'm going to plug in a 2. This purple looks out of place now. I'm going to plug in a 2, so 8 minus 1 is 7. And 4 plus 5 is 9, so 7, 9. So 1, 2, 3, 4, 5, 6, 7. And then I think this is 9 up here because I think it's a 10 by 10. All right, so sketch the graph and find the Cartesian equation that describes the curve it traces out. All right, so these vectors are pointing to the coordinates that are on the line itself, but the vectors themselves are not part of the line. All right, so what I have to do now is connect those points. Come on, you son of a gun. Connect those points. That would be my line. The vectors, and this is the vector valued part of it, those vectors kind of serve as braces that hold that line up. All right, so you kind of look at them as supports to hold that line in place. Right? The more vectors I get in there, the more sure I'm going to be about the overall structure of this thing. But those vectors are pinning that line into its position. Now, because this is in 2 dimensions, I don't think we really needed that concept in order to really convey the idea. But you could see how, looking at it in 3 space, it would take on different meaning. I also need to come up with the equation of a line that exists here. So I could do that one of 2 ways. One way would be by points, and the other way would be to go back and do some substitutions. I don't like the idea of substituting like in Unit 1. What I would prefer to do is just find the slope between these corresponding points. So a little change in y or change in x. So we're talking 4 over 8, so 1/2. And then just choose a coordinate, doesn't matter which one. I'll take this one. And put it into my point slope form of a linear function. Y equals m times x minus x sub 1 plus y sub 1. So we'd be looking at y equals 1/2 x minus 7 plus 9. All right, so we're able to snag this out, not based off of too much of what we did in the first unit, which would be solving for x in the first equation to plug it in for y in the second equation. It wouldn't be like that really at all. It's more so I'm going by points at the at this juncture. All right. So I'm going to put a star on numbers 2 and 3. So I exercised my teacherly right to do the really easy one in class to give you a sense of how it all works, and then leave the terrifyingly complicated one for you to do on your own. I will tell you that your best bet for attempting this kind of question would be to stick to unit circle numbers. Makes life a whole lot easier. All right, so, and what I mean by unit circle numbers is as you go around the unit circle, look for the values of theta that are convenient for both sine and cosine, which really just ends up being the ones on the axes. All right, so don't get into your pi over 4s, you can have decimals everywhere. Just go in quarter terms, so 0, pi over 2 pi, 3 pi over 2, 2 pi. All right. Now, it's going to be an infinite relationship, but you may have to do a cycle or two before you can see what's going on. I just mistakenly gestured what the shape is supposed to look like. I kind of want you to discover that on your own. So I'm going to stop talking. All right. So it's supposed to be like a pleasant surprise. Oh, look what I just made. You know, so that's where I'm going to leave. So we're on to page 39. We got these babies here. These are some good problems. I used to ask people to graph something like this on the test, and then I realized that a terrible graph and a beautiful graph look pretty much the same. And so there was really no value in it. But there is value in learning how to create the graph itself, because it has the look of something that is circular, right? So when we talked about polar equations way back when, right, it was cosine comma sine in some capacity, right? So unit circle values, cosine comma sine. So we have a cosine comma sine. There's a coefficient there, but that's not really going to change things too much. But that presence of the t, that's going to impact the overall shape of the thing. So we're going to make a table of values. Oh, apparently I couldn't recognize that as an attempt at drawing a line, so that sucks. Shot at my self-esteem. All right, so t, we need cosine. And then 2 sine t. And so I'll make the table and then we'll write our ordered pairs, because t is actually going to be the last value, but we need it to be our first value in order to figure out what the cosine t and 2 sine t are. So it's kind of annoying in that regard, but it's still doable. Now, cosine and sine, they're unit circle type values. When I'm selecting my t's, I want to work with the most convenient t values for both cosine and sine. So automatically that's taking me to quadrantals. So just axis angles. So 0, pi over 2, pi, 3 pi over 2, 2 pi. There's nothing wrong with selecting other angles, but then you're going to get into radicals and decimals and things like that. That's fine, but you can get what you need just from these values. All right. If at any point you think you need more, then chuck in a few more and everything will be fine. All right. So cosine of 0 is equal to 1. Cosine of pi over 2 is equal to 0. Cosine of pi is negative 1. Cosine 3 pi over 2 is 0, and then back to 1. All right, the distribution for sine is usually 0, 1, 0, negative 1, back to 0, but it's double. So instead of 0, 1, it's going to be 0, 2, 0, negative 2, back to 0. All right, so each one of these corresponds to a vector. The way the vector is distributed out, really, I mean distributed in terms of like a distribution, not like in terms of an operation, is the cosine comes first, then the sine, then the t. So 0, 2, pi over 2. Negative 1, 0, pi. 0, negative 2, 3 pi over 2. 1, 0, 2 pi. All right, so I labeled up the x-axis, y-axis, z-axis on the paper already, but in terms of the scale, that's really up to you. For the x and y, we're already good to go. Those are just, I mean, they max out at 2 or negative 2, so that's okay. But for the z's, it seems like it's going in terms of pi's. All right. So I'm going to label up my z-axis the way I would if I were creating a trig graph. I'm going to go from 0 to 2 pi. So 0, pi over 2, pi, 3 pi over 2, 2 pi. So I'll just label the important ones, otherwise it becomes messy. Here's 2 pi. I put an extra one there for the just in case factor. I need more. I'll put more. Okay. 1, 0, 0 is going to be easy enough to plot because that's no change in y, no change in z, 1 unit of change in x. All right. So I'm going to plot a vector going to that location, and I'll plot a point at the end of that vector. All right, the second one is 0 in the x direction, 2 in the y direction. So let me get 2 in the y direction. And then pi over 2 in the z direction. All right, so we're going to have to ballpark it, but we know 2 in the y direction, and then the equivalent distance of pi over 2 in the z direction shifted upward from the y-axis. So it's going to put you right around here, kind of floating in space. Dead battery. So we're looking at this point right there. I'm going to use my line draw tool. So that's that point. All right. Next one, -1 in the x direction, 0 in the y direction, and then pi in the z direction. So get a really kind of thin looking. Here's -x. And I'll get -y because I know I'm going to need that in a minute. Undo. So 1 unit in the -x direction. Just going to put it about right there. And then I'm shifting up pi. All right, so again, just estimate what pi looks like and then shift upward from that -1. So it's going to put it like right around here. Maybe just a smidge below that little tick mark. So like right there. Well, I'll make that a black point. All right, so I got that point. Then I need 0, -2 in the y direction, and then up 3 pi over 2. So again, we're just ballparking. A lot of ballparking. All right, so the equivalent distance to 3 pi over 2, which is about this, going up from there. So you got a little landmark here. That top tick mark is about where I'm aiming for. Okay. And then the last one is 1, 0, and then 2 pi. So I know where 1, 0 is, but now I got to go 2 pi up from there. So that's going to put me kind of like right here. Okay, so right actually smack dab in the middle of my 2 pi label. All right, so I'll plot a point there. So we look at that and say, whoa, all right, what's going on here? it doesn't look like it's shaping up to be any kind of recognizable figure. But what we're going to do is we're going to connect the points in the order that we plotted them with a smooth curve. Right? So I'll get a relatively thick smooth curve to kind of hide all the disgustingness, but it looks something like this. So actually I'm aiming for the wrong one. It's going like this, and then it skips that one, and then comes up and grabs that one. Right? But then it makes a turn and comes back and grabs that one. Right? And so you're like, oh, what's going on here? Now, if you were to plot more points, you'd see that this is going to continue its journey this way, and then start the pattern over again. All right, but you only get that by plotting actually more points. All right, so you're ending up with something that's kind of like a spiral staircase, but, and you can see what I was saying before, like you're not going to get in a hand-drawn diagram what you would get with technology, right? But we got to start somewhere, and this is where we start, all right? This is basically the graph of a slinky, but it's an elliptical slinky. All right, so it's not perfectly circular, it's more oblate. All right, so it's gonna have that elliptical look to it, but it's basically gonna be a stretched out slinky. All right, if these coefficients were the same, then it would be circular, and then it would be actually the stretched out circular slinky. All right, so what we're looking at here is known as an elliptical helix. Change this size. All right. There are also circular helixes. So what's the difference? Just general shape. It's going to look a little bit more circular if you have a circular helix. All right, so what I'll do is on GeoGebra, I'll plot this for us so we can see what it's supposed to look like, because, yeah. You look at that and you're like, yeah, okay, I guess.
You're plotting what's in the carrot looking brackets.
Exactly. So digital link. So that's what it's supposed to look like. Not quite what I'm able to produce on paper, but generally, and you see, if you get a top-down view, it looks like an ellipse. All right, but you see that that's really what we're up against. All right, but again, drawing a three-dimensional figure on a two-dimensional piece of paper, or a two-dimensional surface, it's not the easiest thing in the world to do. So obviously, the more complicated the three-dimensional surface that you actually have to draw, the more likely it is going to be that all you're going to end up doing is producing a mess on a piece of paper that doesn't really tell anybody anything, right? Unless, I mean, there are some people out there that are really artistic, and I've had people turn it, like when I said I put this on a test, and it was like disgusting mess from everybody. I just flat out gave everybody full credit because I'm like, yeah, I guess it's right. Well, it looks like crap. Except for like one or two students who are like, I don't know if they're like cartoonists in like their life outside of academics, or just interested in art, or really good at doodling, but their elliptical helixes looked glorious, like better than these. And I was like, I don't even know how you did that. Like conceptually, it's just beyond anything that I'm capable of. But that's what it's supposed to look like. If anybody can draw that on paper, by all means. I mean, like when you see it like this, yeah, I mean, anybody can do it. Like I can do that. But to make it correspond with the points that we calculated, that's what the challenge is.
What is your x? It starts at the x, right? The x coordinate is 1. I don't see.
Yeah, so there's my x-axis, but I can also change my settings.
X is going up.
Let me do my units in terms of pi. Actually, let me get rid of this grid. So I started my t values at 0. So my first point was this one right here. And actually all we got was up to like here. And we had to kind of infer the rest of it. Okay? But the benefit of GeoGebra obviously is you can extend your domain. All right, so that's an example of a more complicated vector value function in terms of how to draw it, but in terms of like the calculus of it, that's even not that difficult, because when it comes to taking derivatives of vector value functions, you're really just taking the derivative a piece at a time. If you're finding a limit, you're finding the limit a piece at a time. If you're addressing continuity or finding antiderivatives, you're doing it a piece at a time. Right? So when they ask us to evaluate, that's plug and chug. You're just substituting in. But when they ask you for domain considerations or restrictions, they're asking you to look at each individual piece and evaluate continuity for each of those components. So, to answer this question, first thing I would do is, well, R of 0. So 3 tan 0 I plus 4 secant 0 j plus 5 times 0 k. Tangent of 0 is 0. All right, secant of 0 is equal to 1. So this is really, after all of this, just collapsing down to a 4j. All right, you do it in your calculator if you want. If you know all the values, that's good too. The secant one is easy enough because it's the reciprocal of cosine of 0, and we know cosine of 0 is equal to 1. So pi over 2, I'll write it out, but you'll see how we don't really have to write it out in every case. 3 tan pi over 2 I plus 4 secant pi over 2 j plus 5 times pi over 2 k. All right. Now, this is just going to flat out be undefined. And the reason why is because part of it's undefined. Well, parts of it. Right? Cosine of pi over 2 is equal to 0. Tangent is sine over cosine. Secant is 1 over cosine. In both of these cases, we're going to have cosine in the bottom of a fraction, cosine of pi over 2. Denominators are going to be equal to 0. So it's undefined because the components for I and j are undefined at those values. And all it takes is 1. If it happens that it's undefined in more than one component, that's fine, but all it takes is 1 component. All right. So then 2 pi over 3. So just rewriting the same stuff. Now I'm just writing all this stuff for note-taking purposes because the reality is some of us know these ratios and some of us don't. If you know them, then you can pop them in right away. If you don't know them, then you're going to have to do an extra step involving calculation. Either way, you're going to get it. It's just a question of how many steps in the process. All right. So some of us, if you know your ratios, then you jump right to the final answers in all of these cases without writing any of these things out. If you don't know the ratios, then you would want to write it out and consider, okay, what is this equivalent to? What is that equivalent to? And so on. Right. 2 pi over 3 is in the second quadrant where tangent is negative. All right, so we're looking at 3 times negative root 3 I. All right, because it's sine over cosine. So at 2 pi over 3, the sine value is root 3 over 2. The cosine value is negative 1/2. Simplify, you get negative root 3. Or it could just be memorization. 4 times, well, the reciprocal of the cosine value at 2 pi over 3. Well, cosine at 2 pi over 3 is what? Hint, I just said it. Negative 1/2. So flip it, you got negative 2. Close parentheses in red. The last piece is just straight up multiplication, so 10 pi over 3, k. All right, so here it looks like it's going to exist for all values. Just got to clean it up a little bit. Negative 3 root 3I minus 8j plus 10 pi over 3 plus k. Okay, so the follow-up question is, are there any domain restrictions? You know, on a test I'd be more specific because that really looks like a yes or no question. Okay? Based on the work that we did, the answer is yes, because of r of pi over 2. All right, but you know that you'd be responsible for a little bit more than that. So what we would want to know is what those domain restrictions are. All right, so the only thing is we don't have to worry about negatives under radicals. The only thing we have to worry about is whether the fraction is going to be undefined. So r of t is undefined when cosine of t is equal to 0. All right. So the restrictions would be t cannot be equal to pi over 2 plus pi k, where k belongs to the set of integers. All right, so any multiple of pi units away from pi over 2. Right? Because that'll put you on the y-axis.
Equals or not equals?
Say again?
Equals or not?
Oh, not equals. All right, so that allows for it to be 3 pi over 2, negative pi over 2. It allows you to go in any direction in a number of different half terms. All right. Notation, we're going to use this notation more and more, especially when we start talking about multivariable functions. So just a quick refresher, that funky looking E, that stands for belongs to the set of. Right? I defined K as my multiplier here. You can use anything you want. You can use N if you want. That Z with the double diagonal there, that stands for the set of integers. All right, so this translates to Z belongs to the set of integers. K belongs to the set of integers is what I meant to say. K. I'm going to say I alluded to this, but I didn't really allude to it. I just flat out said it. It's the same as it always was, except you're doing it a piece at a time. So if I want to find the limit for a vector value function, I'm going to find the limit for each piece of that vector value function. All right. If I want to find the derivative, I'm going to find the derivative of each piece of the vector value function. Antiderivative, same deal. All right. So it's really not that challenging conceptually, but you still have to carry out the process. All right. So if I give you something like a vector value function that contains a natural log and I ask you to find an antiderivative, and you don't know what the antiderivative of the natural log is, then you might have to integrate by parts. So the concept itself is not hard in that, oh, I just have to take the antiderivative of each piece. But then if you run against something that is challenging to find the antiderivative of, then it's a different story. But we're not there yet. We'll get there in a couple minutes. Here it's just a matter of saying, I want the limit as t approaches 3. So I'm gonna apply direct substitution. So it's gonna be equal to 3 squared minus 3 times 3 plus 4 times I plus 4 times 3 plus 3 times j. So 4i plus 15j, 5 threes. So I'll pop a little star on number 2. Now number 3 has that little extra ingredient related to continuity. That one I'll take you through because people forget how to test for continuity. It was kind of a big deal for 5 minutes in Calc 1, and then it ended up not being a big deal anymore for a long time, and now it's going to be a huge deal moving forward. All right, whether a function is, I mean, most people remember the main idea. If a function is not continuous, it's not differentiable. All right, so we want to address continuity because if I'm interested in finding a derivative of a function, I want to know where the derivative is going to be relevant. All right, but it's kind of a lost art to determine what the actual values that are continuous or discontinuous would be. So we're going to find a limit as t approaches -3 of r of t, which is just plug and chug. So -3 comma -3 squared plus 1. So -3, 10. All right. Now, independent of the concept of a limit, what I'm going to do is just evaluate the function r of -3. Now, if a function is continuous, it should feel like you're doing the same calculation repeatedly. You're like, I'm just doing the same thing again. Right? If that's the case, then odds are what you're dealing with is continuous. Right? So that's what's happening here. When I evaluate the function, I get -3, -3 squared plus 1. I get the same thing. All right. So for part C, the answer is going to be yes. And that's because the limit as t approaches -3 of r of t is equal to r of -3. All right. So that's going back to the process that really, honestly, this process I got from my Calc 1 notes. All I did was I copied and pasted it, and I changed my F's to R's, my X's to T's. You get the idea. So I took the F of X notation, made it R of T notation. That's the only difference, all right? Because you need to show that a point exists, right? If it's going to be continuous, the point has to exist, right? Because if it doesn't exist, there's going to be a hole, there's going to be an asymptote or something like that. You need to show that the limit exists, all right? Now, you can have limits that exist, but they're not finite, all right? So the two sides of an asymptote, they're both going to infinity. The limit is infinity, all right? So the limit exists, it just happens to be infinity. But what I need is that the limit, for the limit and the point that exists to be the same thing, all right? So we're talking about two parts of a graph coming together at the same location, right? That's all this process is telling us, right? But now we're expanding it into the vector context. And so that allows us to expand it into 3 dimensions and 4 dimensions and so on, right? So it's taking something that we already know from Calc 1 and building it up. All right. Now, D is kind of sort of reminding us that the limit definition of a derivative is still a thing. All right. This is kind of like a little piece of it. You know, f of x plus h minus f of x all over h. Okay? I don't really like spending a whole heck of a lot of time worrying about that in this class, but I do want to take a second and remind us that that is still a thing that can be done. All right, so we can substitute expressions into vector valued functions just like we can with numbers. All right, so instead of the t, I'm going to put a t plus 2. From that, I'm going to subtract r of t. When you simplify, you get 2 comma t plus 2 squared minus t squared. Now you can clean that up if you want, but it's not really necessary. It's really just getting at the idea that not only can you substitute numerical values into a vector value function, you can substitute expressions in. And if you can substitute expressions in, then the limit definition of a derivative would apply. If that's the case, then all the rules for derivatives and antiderivatives would also apply. Power rule, product, quotient chain rule, implicit differentiation, log differentiation, pretty much anything you can think of. All right? And then everything that goes with antiderivatives could apply. So integration by parts, partial fraction decomposition, just everything. All right, so unfortunately, that means that you got to kind of be prepared. I mean, more than kind of. You got to know your stuff. You got to know how to take a derivative or antiderivative. But that doesn't mean I'm going to beat you over the head with like one obscure antiderivative rule after another. But it is possible that you could have to integrate by parts for a question on a test. Right, so you gotta be ready for that. But we're gonna review some of that stuff, so it won't be the end of the world. So the calculus of it is really just a reminder, like I was saying, that the limit definition applies. So that's all well and good. I'm not doing that, right? Because really what it is the limit definition of a derivative for each part separately. So that f of x plus h minus f of x all over h from Calc 1 for this piece, then separately for this piece, then separately for that piece. All right. It is the definition of a nightmare. Right. So not going to do that, but what we can do is identify the domain. Right. Looking at this, I see that there is considerations for the domain. And then I could also find the derivative. So natural logs, any kind of log, you can't take log of 0, you can't take log of a negative number. So t minus 1 has to be greater than 0. All right, this part of the log. So that means t itself has to be greater than 1. All right, so we got that piece. The sine function I'm not worried about because the sine function is everywhere continuous. You can rely upon prior knowledge. Like, you don't have to reinvent the wheel. If you know something is true, like polynomial functions are always continuous. You don't need to prove that every single time. Okay? But the tangent is sine over cosine, so sine of e to the t over cosine of e to the t. Right? It's a fraction. So that means I can't have 0 in the bottom of the fraction. Cosine of e to the t, that cannot be equal to 0. All right. So for this one, it's a little funky because you're like, well, how the hell am I supposed to figure this out? You know, because we could say that cosine of pi over 2 is equal to 0, and every multiple of that. All right, so that's fine. But we also have to account for the fact that the inner function is e to the t power. So there's that component that needs to be addressed also. So there's a couple of ways to handle it. One way is to just rely on stuff that we did already, and that is that cosine is only going to be 0 when you're dealing with pi over 2 plus pi k. So what that would mean is that e to the t power cannot be equal to pi over 2 plus pi k. All right. But I still need to know what t can be, not what e to the t can be. All right. How can I release that t from the captivity of the exponent of e? Natural log both sides. All right. So we're going to take the natural log of both sides, and that's going to give us t cannot be equal to the natural log of whatever's on the right-hand side. All right, natural log of pi over 2 plus pi k. And again, I didn't write this out before because I knew I was going to write a bunch of other steps where k belongs to the set of integers. All right, so those are all the values that t can't be. Couple that with all the values of t that can exist, and you have your full domain. So all through this mess, we have addressed the restrictions on this function. All right, it will not exist for any value of t 1 or below, and then also anywhere where I have a natural log of pi plus pi k that falls in this interval, that's also going to be restricted. All right, so if you wanted to have a nice, I was going to say a nice, concise way of writing it. I don't know that you would necessarily call what I'm about to write nice and concise. I'll just say a way of representing your complete answer for the domain all in one expression. Squiggly brackets, I would be stating that my variable is t such that t is greater than 1 and t cannot be equal to the natural log of all that crap. All right, so you're kind of just getting it all in one shot. And normally I'd write the where k belongs to the set of integers, but I already wrote it, so I didn't include it. But yeah, that's hideous. But it's also stuff you have to keep in mind. Now, am I going to ask you to state the domain in every problem? No. But you do need to be aware of the domain. Because if I say find the derivative at a particular point, and that point doesn't exist, and you come up with a value, you're wrong. All right? If I say find r prime of 0, like even if it gives you something in the derivative, the function doesn't exist at that location, so the derivative doesn't have any meaning there. All right? So now usually, if it doesn't work for the original function, it's not going to work for the derivative anyway, but there is that gray area. You don't want to fall into those traps. All right, so r prime. So I still have to do that. You know, you're like, well, that was a tough problem. Moving on. Well, now we got to answer the second half of it. Find the derivative. So each piece, we got a little chain rule for the first part. So sine of t squared, well, derivative of sine is cosine. So cosine of t squared times the derivative of the t squared, which is 2t. So that's my first piece. The second piece, I'm going to highlight the two factors that make up the product. Product as in product rule. So the first t minus 1 times the derivative of the second. So derivative of my second function, 1 over t minus 1, which will simplify, plus my second function, which is just the natural log of t minus 1, times the derivative of the first function, but with respect to t, the first function has a derivative of 1, so I don't really have to worry about that. And then for the last part, yeah, we need to know facts. What's the derivative of tangent in general? Secant squared. So secant squared of e to the t. It's chain rule, so I have to multiply by the inner function's derivative. Derivative of e to the t is e to the t. Derivative of the exponential function is the exponential function itself. All right, now if there's a constant multiple, you might have to multiply by that, but that's not the case here. All right, so that's actually our derivative. Now, in terms of level of difficulty, I mean, it seems pretty crazy, but really, if you think about it, it wasn't that bad. It's just a lot of stuff to write. I'm not big on making people simplify without cause. All right, like let's just put it this way: if I ask you to find a second derivative, you're going to want to simplify, not because I told you to, but because you're not going to want to work with this expression in order to find the second derivative. All right. If I'm not going to make you do anything with the derivative, I'm not going to make you simplify it. All right. So you could actually just leave it like this. And in fact, I really kind of encourage you to, because what happens is people go rogue on tests, and it's not like it upsets me or anything like that, but it just makes it take longer for me to grade papers, because I have because I'm lazy. I'm just a lazy person, right? I just want to put that out there. It's not always obvious, because sometimes it seems like I'm organized and stuff like that. But my whole existence is me finding ways to do less work, right? So that's really all it comes down to, right? So when I make an answer key for a test, I don't simplify it, because I'm like, well, I told them not to simplify it, so why would I simplify it? So all I do is I look at your paper hoping that your unsimplified form matches mine. And then somebody, there's always somebody, will take it upon themselves to simplify their work down and come up with a beautiful, simple answer that I now have to determine if it is correct. I don't want to do that. It's a win-win for both of us when I say don't simplify. So don't simplify, all right? If you're told to, that's a different story, but I'm only going to tell you if there's a damn good reason for it to happen, all right? So that's just something to keep in mind. Derivatives of combinations of vector value functions and scalars. So this is where the rubber meets the road here, because we know that we could take the derivative of a vector value function because it's made up of other functions of t. And that, the process is not bad, but then it begs the question, okay, well, what does that mean? Right? Because a vector value function, go back to those graphs, it's the curve that's generated by vectors pointing out into space. Right? So we got the elliptical helix, and it looked wonderful on GeoGebra, it looked terrible on paper, but it's based off of vectors. Each one of these components yields a vector. Then when we connect all those vectors, the endpoints of those vectors, we get the smooth curve. But by taking the derivative, I'm not necessarily getting what I think I'm getting, right? So we have to kind of flesh that out. But we also learned, and this is very important, that there isn't one type of product anymore. All right, back when it was just scalars, a product was a product. You multiply two things, you could use the x or you could use the little dot and everything was fine. But what we're dealing with here are vectors, and so that means that we could be dealing with the dot product between two vectors. We could be dealing with the cross product between two vectors. We could also be dealing with the scalar product, right? So, I'm sorry, a scalar multiple of a vector, but we could also be dealing with some other function of t multiplied by a vector. So all these different ways in which you can multiply vectors, and each one has its own relationship. Now, they're all based off of the product rule in some capacity, but the meaning of these products and their derivatives is really what we're gonna have to spend some time focusing on, right? So that brings us to the implication of zero derivative. So way back when you took a derivative and set it equal to zero and solve, like that was like your go-to maneuver in Calc 1. Man, I have no idea how to do this problem. All right, take the derivative, set it equal to zero and solve. It's probably the way to go, right? Here it's a little bit of a different story. For a vector value function, if the derivative is equal to zero, that means, well, among other things, because you can have turning points at those locations, it also means that you could be dealing with a cusp in the curve at that location, right? So the only way you were going to get a cusp when you were dealing with a derivative, ordinary function derivative, was in the case where the original function existed, but the derivative of the function was undefined. All right? So function existed, derivative was undefined, and in that case, it could have been a cusp or a vertical tangent. All right? Here, when the derivative is equal to zero, that can potentially lead to a cusp. All right? The good news is you don't have to really flesh that out as much as you might have if you were in a class that didn't allow you to use your calculators. All right? So when in doubt, pop it in your calculator, and you might say, well, what about the h of t? Well, just do it for the f of t and g of t and see what's going on with that, because parametric form, you can put the x and y in, see what's going on there, because really h of t is just giving you the height. All right? So see what's going on with x and y. Maybe that's enough to give you a sense of what's going on with the graph overall. All right? We also say that a curve traced out by r of t is smooth on an interval if r is continuous and r prime of t is not equal to zero, except possibly at the endpoints. I'll address that possibly at the endpoints down the line. But it's kind of the opposite of what you would expect in function-based calculus. So all the single variable stuff that you learned back in Calc 1, it's kind of the reverse. All right? So when we're dealing with smooth continuous functions, we're talking about the derivative not being equal to zero. It's when you get into the corners, cusps, and things like that, that's when you're looking at the derivative being equal to zero. At no point have we really talked about tangent lines or anything like that, because how do you find a tangent to a vector? Wouldn't the tangent be the vector itself? All right, because what we're going to need are tangents to the curve that exists at the endpoint of a vector. So that it's a little bit of a different story. So it's a change in the way of thinking. So I'm putting stars on these because really it's just a matter of applying the rules on the previous page. They're products in one capacity or another, but there is like little twists and turns that could kind of streamline the process for you. I'd rather you try to play around with that first before I give it all away. Antiderivatives, same idea as derivatives. You're going to do it a piece at a time. So integrate, and then we have the same idea with cross products. So with that being said, I'm just going to put a star on this because, again, I'd like to see what you can do with it first before I go through it all. So I'll go through all of these. I'm not going to leave it up to you to learn it on your own. I'd like you to try it first on your own before I bore you to tears with the explanations. But the last thing we're going to talk about tonight is arc length and curvature. Well, just arc length, actually. We'll get to curvature next class. Curvature is actually a really fun topic. It's exactly what it sounds like. It's the idea that you can quantify the curviness of a function. All right? Some curves are more curvy than others. Right? So if I tell you that there's a number that will describe how curvy a graph is, you may not know what those numbers are, but you would imagine, I would think, that the number for a circle would be bigger than a number for a line. Right? Circles are curvier than lines. Right? Lines aren't curvy at all, so maybe the number for a line is 0, no curve. Right? Maybe the small circles have a different number than the large circles. Right? So these are some things that we'll get into. But before we do that, we need to talk about arc length. The good news is, it's nothing new. And that's why I can do it in a couple of minutes without rushing it. All right, so what we have here is a circular helix. All right, I know it's circular because the coefficient of cosine and sine are the same. All right, the elliptical helix, the coefficients would be different. All right, so when I'm looking for the arc length, it's really just as simple as taking our arc length formula from parametrics way back in the beginning of the first unit and just adding a third dimension to it. Right? So really, I mean, if you look at what we're dealing with here, it seems an awful lot like the concept of magnitude. And in fact, under Solon, it really is a magnitude. You're looking for the magnitude of r prime. All right? So so long story short on that, I like this formula better because I know what a magnitude is. And as long as I know what I'm taking the magnitude of, I'm going to be in good shape, right? And also, really, if you think about it, a magnitude's a distance, right? So if you're finding a distance between 2 points, you are finding the arc length of the line segment connecting those 2 points. So conceptually, it ties together very nicely. Now, they give us the start and the end point. So S is going to be on the interval of 0 to 2 pi. The magnitude of r prime of t, dt. So I just need r prime. So let me just jot that down here. So cosine has a derivative of negative sine. Sine has a derivative of cosine. And the last component is just a t, so that has a derivative of 1. I'm going to write the 1 in there. Normally I wouldn't bother, but I've seen it happen in the past. I haven't done a study on it or anything, but I don't write the 1. People all of a sudden forget this part in their expanded formula. Okay, so I include it there, and hopefully it'll remind you that that's still part of the fun. Right? So I'm going to find the magnitude of the squared values of each of these components. All right, so we're looking at, on the interval of 0 to 2 pi, the square root of negative sine t squared plus cosine t squared plus 1 squared dt. Now you could just pop this in your calculator, but this is one of those rare instances where doing it by hand is actually quicker than even typing it into your calculator. Okay, and that's because sine squared plus cosine squared is equal to what? 1. So under the radical, I have a 1 plus 1, which is 2. So this is 0 to 2 pi radical 2 dt. Integrating that, I get radical 2 times t on the interval of 0 to 2 pi. So 2 pi radical 2. All right, so like I said, you could put it in your calculator, but this is one of those rare instances that it's just easier to do it by hand. All right, so we'll be doing more with this starting next class. Number 2 is talking about the arc length of this function, which is raised to the 3rd power, which is a little beefier. So for this one, I would imagine you'd be more inclined to put it in your calculator because if there is a rule for cosine cubed plus sine cubed, it escapes me at the moment. So I'm going to go ahead and say that it's not overly likely that many people remember that either, right? And then the last thing here is the parametric equations for intersection of surfaces. I'm going to put a star on that. And just ask you to consider it, not necessarily with the expectation that you're going to be able to go through the whole thing, but at least give it a little bit of thought, because when I go over it, I will tell you that you have all the knowledge and experience to be able to tackle this kind of problem. It's just, it's intimidating to look at. All right, and there's a lot of things going on, but at least if you kind of familiarize yourself with the structure of the problem, when I go over it, it's not going to be, whoa, what the hell just happened? All right, so that's where we're going to leave it for tonight.